I'm Dr. Amanda Clifford, and I'm an assistant professor in the Department of Materials Engineering at UBC. Designing smart surfaces that either kill pathogens upon contact or prevent their attachment are one of the ways we can combat the transmission of infectious disease, such as COVID-19, as well as hospital-acquired infections. So copper is one of the best antimicrobial materials that we have. It kills up to 99.9% of bacteria within 2 hours of contact. In previous studies supported by Teck, Copper and Health, and led by Dr. Elizabeth Bryce from Vancouver Coastal Health and Dr. Edouard Asselin from UBC Materials Engineering, it was found that use of copper in settings such as hospitals and public transit greatly reduced the microbial load on high-touch surfaces. As a result, Teck has generously donated copper patches for use in high-touch spaces around the applied science buildings to ensure all students have a safe return to campus. But one of the disadvantages of using copper is it's very costly to make a doorknob or a hospital bed rail from pure copper. So my research group is developing new ways to modify complex shaped high-touch surfaces with copper. One coating technique that my group is particularly interested in utilizing is electrodeposition. And some of the benefits of electrodeposition is that you can coat complex shapes such as a doorknob with ease, while having a high degree of control over both the surface chemistry and morphology or roughness, both of which dictate the ability of a pathogen to adhere to a surface. Two other considerations when designing these smart surfaces are scalability of the processing technique used to fabricate them, and also durability of the final coating. There's a lot of research activity in the area of antimicrobial surfaces. However, many of the processes used to design these smart surfaces are at the benchtop processing scale, whereas with electrodeposition, it's already used in the electronics and mining industries to fabricate materials, so we know that any coatings we design, we then can scale our product. Durability is another consideration, since these high-touch surfaces will be continually subjected to both human sweat and hospital-grade disinfectants. But again, using electrodeposition, we have a high degree of control over the chemistry, so by tuning that, we can increase the durability and adhesion to the substrate. This technology will improve patient health outcomes in clinical settings by reducing the incidence of hospital-acquired infections. It would also improve public health outcomes by lowering the rate of transmission of infectious disease in public settings, such as public transport, airports, universities, and sports venues. I'm grateful for our partnership with Teck Resources, as well as the financial support provided through their Copper and Health program, so that we can continue to advance technology at the intersection of materials engineering and medicine, which will ultimately lead to safer public spaces and improved public health outcomes.